I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will see the topic Critical Frequency, MUF and Skip Distance for the unit antenna measurements and wave propagation. And the concept of actual height and virtual height is virtual height, the incident and the reflected rays follow paths that are exactly the same as they would have been if reflection had taken place from a surface located at a higher height, called virtual height of this layer. But in the actual height, the actual path of the wave in the ionized layer is a curve and is due to the diffraction of wave. The height from this curve to Earth's surface is called actual height. And the critical frequency is defined as it is the frequency of the layer as the maximum frequency that is returned back to the earth by that layer when the wave is incident at an angle 90 degree to it. The critical frequency for F2 layer is between 5 to 12 megahertz. Its value is not fixed and it depends upon the electron density of the ionosphere. Critical frequency changes with time of day, atmospheric conditions, and angle of fire of the radio waves by antenna. The existence of the critical frequency is a result of electron limitation, that is, the inadequacy of the existing number of free electrons to support reflection at higher frequencies. Critical frequency is the highest magnitude of frequency above which the waves penetrate the ionosphere and below which the waves are reflected back from the ionosphere, and it is denoted by Fc. Critical frequency as a function of electron density is given by the expression Fc is equal to 9 root of n max. Here n max is maximum electron density per meter cube and Fc is in hertz. Critical frequency as a function of maximum usable frequency, Fc is equal to maximum usable frequency multiplied by cos theta, where MUF is the maximum usable frequency and theta is the angle of incident. And now we are going to see the relationship with plasma frequency. So the dependence of critical frequency with respect with electron density can be related through plasma oscillation concept, particularly the cold electrons mechanism, and it is given by the expression omega p is equal to root of n e squared by m squared epsilon naught radians per second. And here the electron charge is we know it is E is equal to 1.602 into 10 power minus 19 coulombs. We know the electron mass in kilograms and permittivity of free space 8.854 into 10 power minus 12 amperes per meter square. And this omega p is the angular frequency 2 pi f. It is 56.415 root of Ne. And so the critical frequency is solved by the expression as Fc is equal to approximately 9 root of n max. And using these default values for electron charge E, permittivity of free space, and electron mass epsilon naught, and charging angular velocity omega with respect to frequency f, this gives n squared minus 1 is equal to 3182.607 n by 2 pi f the whole square. And solving for the refractive index n is equal to root of 1 minus 81 n divided by f square. And the critical frequency and the f layer of ionosphere is all longer distances of high frequency communications use high frequency radio signals that are obliquely incident on the ionosphere. If the high frequency is above the critical frequency, the radio signals pass through the ionosphere at an angle instead of head on. Now the critical frequency changes continuously and the F layer of the ionosphere is mostly responsible for the reflection of radio waves back to Earth. The other layers D interact in two ways, and absorption of frequency and during the day. The D layers forms and the F layer splits into two layers as F1 and F2. The maximum usable frequency in radio transmission, maximum usable frequency is the highest radio frequency that can be used for transmission between 2 points on earth by reflection from the ionosphere at a specified time, independent of transmitter power. This index is especially useful for short wave transmissions. In short wave radio communication, a major mode of long distance propagation is for the radio waves to reflect off the ionized layers of the atmosphere and return diagonally back to Earth. In this way, radio waves can travel beyond the horizon around the curve of the Earth, and it is given by the expression maximum usable frequency MUF is equal to critical frequency divided by cos theta. And the ionization of the atmosphere varies with time of day and season as well as with solar conditions. So, the upper frequency limit for skywave communication varies throughout the day. And this MUF is a median frequency defined as the highest frequency at which skywave communication is possible 50% of the days in a month as opposed to lowest usable frequency LUF. And this is the frequency at which communication is possible 90% of the days, and the frequency of optimum transmission FOT. So typically the MUF is a predicted number given the maximum observed frequency MOF for a mode on each day of the month at a given hour. The MUF is the highest frequency for which an ionospheric communication path is predicted to 50% of the days of the month. Now, the skip distance, a very important concept in skywave propagation. It is defined as the shortest distance from the transmitter measured along the surface of the earth at which a skywave of fixed frequency returns back to the earth. The frequency should be greater than the critical frequency. And the skip distance is kept constant by adjusting the angle of incidence in such a way that wave returns back to the earth. Maximum usable frequency is the frequency which makes a given distance corresponding to skip distance. The frequency should be greater than the critical frequency. Now, the assessment, the maximum possible frequency for which the wave is reflected back for a given distance of propagation in the ionosphere layer is called, we know it is maximum usable frequency. And the skip distance, we know it is the minimum distance at which the waves return back to the earth at lowest possible frequency. Thank you.